Welcome to Unit 2, more function types. And that's exactly what this unit's all about, different types of functions. So let's get into it. The title of this first lesson of Unit 2 is 2.02, Reciprocal Power Functions. You may have heard these words individually, but maybe not all together. So we're going to see and learn all about them. Starting with our goals. Determine the domain and range. Does that sound familiar? I hope so. We're going to figure out the domain and range of a reciprocal power function from its equation. Determine the equations of the asymptotes. What are asymptotes? I don't know. We'll find out soon enough. And again, this is from an equation. And ultimately, we're going to graph these reciprocal power functions. Now, you need to know what a reciprocal power function is, so here's your definition and a few examples to look at. A reciprocal power function is a function that has a fraction. We see fraction, fraction, fraction with x in the denominator raised to a power. It might be 1, 2, 3, or something else, but if it has those things, it is a reciprocal power function. Okay, so here's your parent reciprocal power function where you have your name of the function on the left, f or g or h, whatever the case may be. X again is the input, that's the variable, right? A on top will be some number. Now it can't be 0. Why can't A be equal to 0? Well, then we wouldn't have a reciprocal power function, would we? Because a numerator of 0, what does that make the function, the fraction equal to? If you had like 0 over 2, that's equal to 0. This is very important, but 2 over 0, what's that give you? That is undefined. You have to know the difference. It will make quite a big difference in this unit. So make sure you write that down right now. So let's review a bit about domain and range. That was part of our goals for today. Domain is a set of all possible what values that can be put into the function and produce a number. This is all the possible x values. So what this is really saying is if you can put a negative number in and get a number out, then a negative numbers are part of the domain. If you can put in 0 and get a number out, 0 is part of the domain. If you can put a positive number in the function and get a number out, and you might be wondering, well, what do you mean, get a number? Aren't I always going to get a number? No, not necessarily. Didn't we just talk about an undefined situation? Yeah, you're going to see that pop up, okay? And then range is the set of all possible y values that can be put, again, into the function and produce a number, okay? So with range, we'll get into it more in detail in just a moment, but let's just review a little bit. So domain is all possible x values. So if we have a line like this, hopefully you know that's a parabola that comes from a quadratic function where you might have other numbers and coefficients and things, but it will have the highest power of x squared. So domain is x values. Where do you see x values on a coordinate plane? I didn't draw it here, but you can visualize it. It could be here or there or wherever you'd like. Doesn't really matter for this example. X values they go left and right, right? So we're going to start with the lowest values, which are all the way to the left, okay? So this arrows indicate something, right? What do they indicate on graphed lines? Well, they tell us this goes forever in this direction, right? And it's going mostly up. But we're not worried about up and down right now. We're worried about domain, which is left and right. Is it going at least a little bit left or right? It is. It's going a little bit left, and it will continue forever. So slowly but surely, we're going to have, and this is how you write domain like this, we're going to have all negative numbers. So it's going to go all the way to negative infinity. Okay? And anytime you use infinity or negative infinity, you use parentheses. It's just the rule. Okay? And then how far right will this go? Well, this arrow is going slightly to the right. So it will go right forever. Meaning, any x value you pick, you can plug into the function and you will get a point. You will get an ordered pair because this graph technically will cover every value all the way left to all the way right over time, right? That's what it is saying. That's what we're saying with this domain. Now range, so we go left to right. So we start with the lowest values and we go low to high. Same thing with y values, okay? So let's draw a bit of a graph here, and let's just label the y-axis right there. So range obviously goes up and down with the y-axis, but we want to start with the lowest values, which are at the bottom, right? So what is the lowest y value you see on that graph of any point? Well, I see it here at -2. Is it included? Yeah, that point is going to work. So since -2 is included in the solutions, we use brackets. Okay? And you might be thinking, isn't the point always included? No, we're going to see that very soon. And how high up does this go? This is low to high again. And well, those arrows are going to go up forever in a positive direction. So there's our domain and there's our range. Okay, that is something you will need to practice and get better at. Now let's talk a bit about asymptotes, what they are, how they work. An asymptote is a dashed line. So let's draw a vertical dashed line because there are vertical asymptotes. You're going to see me label throughout the unit as VA. There's also horizontal asymptotes I'll label as HA. Okay? And what these are, they are an invisible line. Okay? Invisible. I mean, we see the dash, but we know dash means it's just kind of guiding us along the way, right? And it's basically a boundary line. So what we're saying is your graph line is going to get closer and closer and closer to that dashed line, but it will never touch. That is a bit mind-blowing, isn't it? But it's true. And maybe with a vertical asymptote, it would look like this. And sometimes it might even look like it's touching. It might get so close based on who's making the graph that it looks like it's touching. But just know, it's not. If there's a vertical or horizontal asymptote, that graph line is not touching it. It's not going to cross it. That's a boundary line, right? Okay, well, if domain tells us all of the possible x values and range tells us all the possible y values, but asymptotes are telling us there's boundaries, does that set limits to our domain and range? It does, right? So there's a very close connection. And we're going to start to discover that right now. We're going to see a graph here of a reciprocal power function. If you've seen something like that, great. Maybe you have a bit of prior knowledge on this. If not, there's a look at it. We have two graphed lines, but that's for one function. That function is right here. I'll write it nice and big for all to see. This is what it is. This is a reciprocal power function. Notice it's positive. Notice the power in the denominator is 1. If you don't see it, it's 1, right? And this is what the graph looks like. We'll get into that more in the future, but let's read. You've heard me say many times that a function's like a machine, right? You put something in, that's the input, the x value, okay? And usually you get something out. You get an output, which is your y value. But occasionally the machine malfunctions and it breaks down. And when does this happen? It happens when the function is undefined. And the good news about that, even though our machine is broken, is that it tells you what the vertical asymptote is. In this example, if you plug 0 into the function, you see the inputs here and then the outputs there. But I'll just work it out here. If we put 0 into the function, we get that 0 in the denominator, which a moment ago we said is undefined. So not only does that tell us there won't be a point at that x value, it tells us there won't be any points along that vertical line. So there's a vertical asymptote where x is 0. So don't forget, even though the x-axis is horizontal, we are labeling our vertical asymptote. It's a vertical line, x equals 0, because any point on this line will make that true, right? X is always 0. Okay? So now you know when a function's undefined and how to find vertical asymptotes. Okay? Another way you can solve them is by taking your denominator, in this case x, and setting them equal to 0 and solving for x. Well, that was easy. It's just x equals 0. It's not always going to be that easy, but this time it was. Now let's practice finding domain and range. We're starting now with domain, okay? And the main question you want to ask yourself when finding a domain is, when I input these types of numbers, negative, 0, or positive, do I get a number out? I'll give you a moment to practice. Okay, so let me be very clear. If we can put in a negative number and get a number out, that means any negative number works and it's part of our domain. Let's see. -1, let's just say, make things easy on ourselves. That's going to be 1 over, well, -1 times -1, that's positive. So we do get a number out. So that tells us negative numbers are part of our domain. So we can already start to write that over here, because remember, you start with the lowest values, and of course, negative is as low as it gets, right? Okay, what else? We have 0. 0, 0. We've worked a few of these out already today. 0 squared, of course, that's just 0, and that's going to be undefined. Interesting. Okay, so 0 is not included in our domain. So what do we do? Do we just leave it out? You're actually going to write it. You're actually going to write it. But why would I write it if domain is showing what I include? Well, we have to somehow say that we don't have values on that vertical asymptote that we found, we can find right now. Set this equal to 0. If you square root both sides, x equals square root of 0 is just 0. So again, there's a vertical asymptote at x equals 0. Okay, so somehow we have to leave that out. And how do we do it? We use a parenthesis. So guys, you use parentheses with positive and negative infinity always, and with values that aren't included. But there's more values, right? Because you're going to find when we put in negative number or positive numbers, you're going to get a number out. So positive numbers are as well. So there's something we need over here, right? Can you piece it together? Well, this is how we do it. We can also say that this is united with, because it's all part of the same function, right? All these domain values. It's united with not 0. So we're not including 0, but we're including every positive value after that. This is your domain. So what happened here? We said all negative values up to zero, not including zero, then all positive values after zero. Sorry, can always be in a guard dog. Okay, so we found domain. Great. Now let's find range for the same function. We're thinking about this differently, okay? So stick with me. Here we go. It's similar, but a little different. Range is the set of all possible y values. I don't see y in the function. So where is it? Well, you should know by now that g of x or f of x, whatever the name of the function is the same thing as y. Okay? It's what you're solving for. It's the output you're going to get. So what else do we need to know? To find the range, you need to input a negative number, a zero, and a positive number, just like before, to see what the machine can produce. Okay? So let's do that. Let's put a negative value. We already did this before. We know this gave us 1 over 1, which is positive 1. Okay, so it's all about what we get out, right? So g of, in this case, negative 1 is the same as y. So can y be a positive number? Yes. We put in a negative number, but remember what range means. It means possible y value. So this is all about the output, about what comes out, okay? So this right here is what tells you that positive numbers are possible. They are part of the range, okay? So we know positive numbers are. Great. So I'm just going to put positive infinity for now. 0? Well, we know that's undefined, don't we? Okay. So I know I'm not going to include 0. And then positive numbers. If I put in a positive number, what happens? Well, clearly I'm going to get a positive number out. So again, positive. So can we get a negative number? Can we get y equals a negative number? No, these are positive. This tells us y is not included, or sorry, 0 is not included. So negative numbers are not part of the range. It's not possible because you're going to square every negative number, and a negative times a negative is a positive, right? Okay, so how do we write our range? Test yourself. Well, we want to start with the lowest value. Lowest value here is 0, and then it's going to include all values in the positive direction after that. Cool, cool, cool. Well, this was 1 over x squared, and here it is on a graph. We see our vertical asymptote, but we also see a horizontal asymptote, which makes sense, right? We see this flat line there because we were told no negative values, right? So notice how low is this going? Just above 0, right? The lowest value is just above 0, all the way to positive infinity. That's for the range. And then domain, we're going all the way left, right? Let's just visualize it for a second. Domain, this arrow is going all the way left, so that's negative infinity, all the way right until you get to this vertical asymptote that it's never going to touch. So that's why we say 0 united with what happens? Well, this line picks up right where we left off, just on the other side of that asymptote at 0, and then this arrow goes on forever. There's a little visual to help you fully understand. So there are asymptotes, our domain and range, they all work closely together. And at this point, you might be thinking, man, do I have to graph these? Like, some of these are pretty weird. Like, we had this with 2 lines kind of separated there, and now we have this one with 2 lines separated up here. What's the deal? Well, yeah, sometimes you will, sometimes you'll need to match a graph with a function. We'll do some of that today, and this is what you need. I know it looks like a lot of information, and it is, but I would say it's going to save you time. Okay? So if this is a positive, I'm not even going to say numerator, positive, and the power is odd, then you're going to have part of your graph line in quadrant 1, another part in quadrant 3. This will be your domain, this will be your range. Okay? Always. But you might be thinking, wait a second, there's a 1 and a 3. These are different. Why is the graph the same? Well, it will vary slightly. Like this line might come in a little bit like that, or it might go closer to the origin like that. But in general, it will look similar. It'll be curved like that with the same asymptotes in quadrants 1 and 3. Okay? And I'm just going to take numerator out of all of these because we're just saying the entire fraction is either positive or negative. Okay? So look this over for a moment, and you'll see some things in common. So here we have positive, positive, odd, odd. That's what your graph will look like. You have negative, negative, odd, odd. That's what your graph will look like. So you kind of have this almost plus sign formation going on, where here you have positive, positive, even, even. Now you have this like rocket ship visual, negative, negative, even, even. This is almost like the Grand Canyon, right? So I'm going to remove all that. I would highly, highly recommend having a screenshot of this handy because, like I said, it's really going to save you some time. And notice we have all the domain and ranges listed as well as the quadrants they're in. If you're ever unsure about quadrants, write the letter C. You start in quadrant 1, then 2, then 3, then 4. And moving on. It is time to graph one of these. We have our reciprocal power function f of x is 3 over x, and the first thing we're asked to do is determine the asymptotes. And we didn't really talk much about horizontal asymptotes, so let's do it now, and it basically requires a bit of logic, okay? So let's think about it. Look at our function. What is f of x the same as, did we say before? Y, right? Okay. So is there anything we could plug in for x? F of 0, f of 1, f of 5, f of negative 5,000, anything at all we could plug in for x that would make everything on this side 0? No, because the numerator would have to be 0, and that's not going to happen ever, or we would not have a reciprocal power function, right? Like we said before. Okay. So if you can't make, if y can never be equal to 0, then isn't that your horizontal asymptote? Yes, sir. Yes, ma'am. Go ahead and graph it. Okay, we have our horizontal asymptote right there on the x-axis. The equation of that line is y equals 0. Now it's time to find the vertical asymptote. You had practice with this already today, so try it for yourself. There's a reminder that you just set the denominator equal to 0 and solve for x. So do that first and then graph it, please. Okay, let's see what happened. Well, it's going to be right there on the y-axis. That's the line x equals 0, right? Because you set this x equal to 0. It's just, that's it. There's nothing left to do. Now, I told you a moment ago that this would come in handy, and it already is. Because At this point, okay, great. I have my vertical and horizontal asymptotes. I could plug values in, get values out, and I could plot some points, which is true. But let me rewind for a second. What they're asking next is to find the domain and range. So that's where I'm bringing this into play, because here we're told domain and range all over the place. So what kind of function is this? Is it positive and odd, positive and even, negative and even? What is it? Well, it's a positive, and the power of x is 1. It looks just like this, right? The numerator is different. Doesn't matter. So we're looking in this area. So there's your domain and range. Look no further. There's your answer to the second part of this question. Again, you could plug in values just like we did before, but this page helps you. That's why I asked you to put it in your notes, because it's already coming in handy. Now, the last thing we're asked to do is graph. So yeah, we are going to find a few points, but this is still easier than doing this work we had to do to find domain and range. Okay, and even so, you're going to use this. Let's say you didn't do this and you're just like thinking, okay, I'm just gonna find some points. That's great, but these graphs are still really going to help you. So we know it's going to be in quadrants 1 and 3, right? We already know that. So now it's time to find a few points. And here's kind of what I'm thinking when I'm going to do this. Here's a graph, let's just say. I know I'm going to be in quadrants 1 and 3, and it's going to more or less go like this, right? Okay. So don't I want some values that are a little further out? Maybe I don't want to pick 1 and 2 because I'm not going to get a full read on this graph. We don't need to find 10 points, but maybe just pick some bigger values. Okay. Now that you gave it a shot, I'll show you the values that I'm going to pick. I'm going to pick, let's go with 5, 2, -2, and 5. Okay. And I'm actually going to do it on the last page because this is already set up quite nice for me. So let's go. Okay, so I picked some values closer to the origin and some further out. Let's see what happens. Actually, these should be 3s, shouldn't they? There we go. Okay, so 3/5, that's going to be 0.6. 3/2, that's going to be 1.5. And then these will just be the negative versions of those. So negative 1.5 and negative 0.6. Okay, beautiful. 5.6, and that makes sense, right? Because think about it, the further out we're gonna go, like over here, let's just say the point's over there, the closer to the x-axis it will be, meaning the smaller the y value will be. Okay, negative 1.5, negative 0.6. Okay, there's our table of values, and now let's actually plot those points. Okay, so 5.6, right about there. 2, 1.5, right about there. We could have picked 1 as well to get an even better read on this, but for now, we know the general look of this will be like that. And then we have -2, -1.5, and oh, this should have been negative. -5, -0.6. And notice there's a mirror effect going on. Where is the mirror? What do you say? The mirror is actually a diagonal mirror like that. Turn your head and you'll see the reflection. Okay, we're not asked to do that, so I'll just remove it, but there is our graph. We did it. But we're not done. So let's talk about the numerator a little bit, which is A in our parent reciprocal power function, right? We see that right there. The numerical value, so whatever number it is of the absolute value, because we're focused on the positive version of it, right? Absolute value is always positive. It affects the graph of the reciprocal power function. It does have an effect. We want to compare now the tables of these graphs to see what is that effect. So here, notice we have the same denominators, but there's something different. We have a 1 and a 2, okay? The green line has 1. Notice, the smaller the numerator, the closer this green line is to the asymptotes, right? And the smaller the y values are, right? This point was here, now it's down there. This point was here, now it's down there. That's true for all points, okay? And there's a few more reasons, so let's read about them, okay? So the smaller the a value, the smaller the number is on top, like I just said, the smaller the y values, the tighter the function is to the intersection of the asymptotes, which is right here, right? Everything's coming in a little closer to there, right? And the faster the branches approach the asymptotes, right? So kind of the same thing, just said in a different way. Something to keep in mind. Now, there's several similarities and several differences, and I'd like you to see how many you can come up with. Pause this and make a list to explain how these compare. This is my list. Yours might look similar or a little different. I'm listing all the key important things, and I included the graphs. So the domain, the range, I'm saying it's reflected over the x-axis in relation to its positive form. So notice it's negative, right? So the positive form was like this. But the mirror on the x-axis flipped everything upside down. Okay, it's a reflection over the x-axis. These graph lines are in quadrants 3 and 4. We see a horizontal asymptote at y equals 0, just like before, and a vertical asymptote at x equals 0. What about this one? Domain is the same. Range is different though, so let's highlight that. This range goes from -infinity, it goes down, right? That's why it's going from -infinity up to here. So those are the y values, our range. This range is 0 to positive infinity. So because this is the positive version, those lines go up. So I'm highlighting the range area. Okay, of course that goes up forever over here and down forever over here. Of course, that also means it's in different quadrants, 1 and 2. So I'm highlighting the key differences. This is in 3 and 4. But the asymptotes are in exactly the same places, and it's not reflected. Okay, we are down to our final problem. We're matching a function with a graph. And once again, you're going to want to use that handout we looked at before. I'll remind you what it looked like right there. Take a screenshot now if you didn't before. So which function is graphed? You don't have to do much work. If you have that handout, that does the work for you. I did the work for you. I put that together. So use it, please. And we see the graph lines are in quadrants 1 and 3, so this is positive and odd. And that's it for today. Complete the 2.02 on your own in the OLS, and that's it for reciprocal power functions.